here and also in Kaust. And this is a counterflow flame, and then they basically put an electrical field, and from just in this direction, you can see when you increase that the voltage or you increase that the strength of the field, you can see clearly that the stagnation plane moved, and then the flow pattern changed. No longer this kind of stagnation flow anymore. There's some kind of vortex here and vortex there is the internal flow, just like that the pattern of ionic wind. And he plot a very simple geometry to show how that the electric field and the motion of negative and positive ions is causing this flow pattern. As you can see from here, initially that you have a flame stabilizing in the middle. But as you put a electrical field and you have this positive ion, which is a blue, and moving towards that the cathode, and you have the negative ion moving to that the anode. So you have something in from the flame. The flame is like a source of flow, and the positive ion move that, and negative ion move that, because the flow speed of this ion generated is bigger than the flow speed of the stagnation flow. So you are forming a new two stagnation. One is on this oxide side, the other one is on the fuel side, and in the middle you generate this suck in, because most of the ions they move, and then you have some kind of fresh air to substitute this motion about the neutral molecules and ions. So therefore, you're causing this kind of recirculation, and form two stagnation. One is here, the other here, and then the flame is sitting between. So this is a very dynamically, I think it's very interesting. And but if you understand how the ionic wind act, it's pretty clear. And what is the mechanism, right? You just need to remember there are two types of ions, positive and negative. If you only think about the positive, then you cannot explain this, right? But the positive is more strong. That's why they push that they flow like that. The negative ion clearly is weaker. You can have a smaller effect on that. And so the negative thing he did, what about the AC effect? He just said, instead of doing DC, the question maybe you ask, or maybe you ask, what is that the frequency matters? And from there's no electric field, you can see that this particles is here, and then you have flame sitting in between. And then when you have a 2 kilovolt at 10 hertz, which is very low in between them, and you start to see that some kind of ionic wind push this flow going there for negative ions, and positive ions push this one. If you increase that the frequency, that it means that you put more energy there, right? So that means that ionic wind is become strong and strong both sides. But if you increase more, and 1,000 kilovolt, you can see they come back. Means that the ions cannot be responsive that fast to the frequency. So your ionic wind effect is suppressed. So when you try to using ionic wind, try to control something, the things you remember from this figure is that do not use a high frequency one, right? And the lower frequency or DC is more effective. Short pulse probably more effective, and to create ionic wind to control the flow. And the question really that in this kind of electrical field and on flame effect, it's not just the interest of the flame shape, changing in the wind. Rather that the combustion people try to ask the question, does the electrical field really change that flame speed? And if it is yes, how? One way that I create ionic wind, but ionic wind cannot really generate much thing. It only generate dynamics. The other way that in the electric field, I generate electrons. The electron might be able to collide with the fuel and break down the fuel and enhance flame speed. Third is that the electrons collide with the molecules and exchange energy, may generate heating and enhance the flame speed. In early 70s, a lot of people studied how does electric field. They put a DC electric field, put a microwave, and they see how before the breakdown, they see how the flame speed is increasing. Somebody say increasing, somebody say it's not increasing at all, And it's a totally different observation result and published in Combustion Flame, and probably is the 70s and 80s. So here is that experiment also by Professor Chow. I think this is a very interesting experiment. What he did is that he said, okay, I have a channel that I put an oxidizer from the top and I put a fuel from the bottom. And because this is a mixing layer, I potentially can create this kind of age flame, right? You got a lean premix flame there on the oxide side. You got a rich premix flames here, and you got a major diffusion flame tail along, and then you have a concentration gradient of the fuel. So this is how that the flame propagate in this kind of age. So if you have a 2 kilovolt, and this is what a 0 kilovolt, you can see the flame is flat. You have negative 2 kilovolt, its flame is a little bit tilt up, and then you have positive and a little bit tilt down. It's clearly, this angle is caused by ionic wind. But the question to ask is that, will the flame speed change, right? If the flame speed does not change, it's solely fluid mechanics effect. And for wire, and people really don't know what is the effect. And then what he measured. He is a very careful person, and he measured also the electric field. He probably computed or measured it, and then he measured 3 different speeds. One is that displacement speed. The displacement speed is that the flame motion and in the channel, that's called displacement speed. And then he measured the flow speed, which is that the UU is unburned gas in front of flame. The difference between these two, the displacement and then flow speed, will be the flame propagation speed, right? Correct? So what he did is that he measured this, and this is that the displacement speed, and this is the fluid mechanics speed. The difference between these two will be that the age flame speed. You see some kind of effect caused by that electrical field effect is a DC. And what he concluded is that ionic wind and is causing the secondary flow modification is a more important factor. It reduces the displacement speed when you increase that the DC. You see, whether it's negative or positive, the displacement speed decrease. Why? To me, it's very easy to understand, because that with the flame is a propagation in this direction, and you put a electrical field in vertical direction. What does the ionic wind do? The ionic wind will bring the negative ion out of the flame, positive ion out of the flame. All these ions and the neutral molecule, they have a high enthalpy after the flame, right? So if you try to move them out, what do you mean? You mean I'm losing my energy from the burning gas, correct? You create a temperature rise in the flame and then significant decrease of the temperature because of the ionic wind. Then you generate more heat loss to the flame. And then the flame speed should decrease, correct? So this is that if you do this experiment, the result will be like that due to that the transfer. It's very simple. And indeed, he did this a compare that with AC and with I guess probably different frequency. If we're looking at that lower frequency, and here that is a displacement speed, and here is that with different voltage. As you increase the voltage, and then ionic wind is strong, and then in the end, what you do, age flame speed is everything is decreasing. So what do you say that the ionic wind plays a major role that to enhance that the heat loss from the burning gas, and then reduce that flame speed? That's simple, right? But the question is, that is not interesting, and in terms of a conclusion. The trust is most of people try to use a microwave or electrical field to enhance the flame speed. Most of the observation before they saw is that flame speed is increasing, and this experiment basically shows the flame speed is decreasing. It's a contradictory result. If one of them is wrong, of course, they're not. They're experiments, right? There must be the way, how do you explain it? So the way explained is because this is that the ionic wind is basically play a role that for heat loss, enhance heat loss. Of course, flame speed will decrease. But if you play another role that increases that electric field strength, another mechanism, which is that electron impact energy transfer will play a bigger role. They will raise their temperature and then enhance their flame speed, right? So that's what the experiment and we did and a long time ago. Before we do that, you see the DC electric field is Air Force, Camcorder and Ganguly, and about 9 years ago they did this kind of flame and instability. All these kind of things is due to the ionic wind, flame instability, and also people. And for me, if you're looking at the instability, about Rayleigh-Taylor instability, if you do a very simple linear analysis, you can see that this is a Coulomb force. Once you have a Coulomb force, this Coulomb force play a role as a gravity acceleration potential. That potentially change your growth rate of instability. So if you have interest and you go back to review that the Rayleigh-Taylor instability and you put a acceleration effect, and you would find an equation something like that. So understand the ionic wind, the scale. The scale is bigger than the flame speed, and the scale is bigger than the mixing layer, stagnation flow velocity. So you would expect that the ionic wind has a potential that enhance the fuel and air mixing to reduce soot, correct? So this is an experiment and the same by S.S. Chong and Char, and when in Korea, you can see this is that the sodium flame, a diffusion flame. Once you put this enhanced electric field, and the flame, of course, is subjected to a ionic wind, and the ionic wind enhances mixing. Eventually, the soot is reduced. So you can play a lot of tools using ionic wind to control that the soot. I was consulting to a company in Seattle, and what's the name of the company? I forgot the name of the company, but they have almost 20 staffs. Probably 15 of them are PhDs. The entire research group was doing ionic wind, try to control the flames in a burner of housing, a heater of your house, natural gas. Try to do that to reach an in burn, and they probably raised quite substantial money and there. But it was really difficult to control this because the ionic wind is really dependent on your size of the flames, and then the turbulence scale and the electrical field is you can control in one direction, in one condition, but you may not be able to control another direction. So basically that is what's difficult to control. So when I went there to ask me the opinion about what is the research future, my advice to them is stop doing this. So because if you try to generate flow velocity, try to control the flame stability, you have much better way using mechanical engineering to do that. You don't have to use an electrical field to generate ions, and that is really not right. The good use of plasma is using the kinetic effect that can do something that you normally cannot do with a mechanical effect, right? For mechanical engineering, we are really good at mechanics, but we are trying to learn chemistry to try to using a chemistry way to enhance the effect. So I saw the company, after 2 rounds of reviewing, they basically changed their direction and they try to focus on the chemistry effect and of the plasma interaction to control the combustion. So here is the effect when I was, you see my Dick Myers and me, and we were 10 years ago. We tried to see, does the electrical field really can enhance the flame speed? If it is, what is the mechanism? So what we did is that we built this kind of a microwave cavity, and this is a microwave guider, and this cavity has high Q. That means that the losses is minimized. And then this is that in the bottom we have some kind of a flow, and the flame is here. When you turn on the microwave in this direction, you can see that the flame move upstream. But you look at the number here, 2.6 kilowatt. I only increased the flame speed by 50% probably. So that energy is bigger than the energy of the flame itself. The flame is only probably several hundred watt, and then I need 2.6 kilowatt in order to move the flame a little bit. So I look at this number, I said, my God, Jesus, this might be really impractical to use a microwave to control flame stability, right? So what is the cause of it? And then if you're looking at that literature data, there's a lot of a measurement of methane air flames. It's lean at let's say equivalence ratio 0.7. You put it's a microwave. Like you put a 2.6 kilowatt, 400 watt, 1. It's a kilowatt level. It's a high cavity, high Q cavity. So the flame speed increasing 60 to 80%, 21% is only about below around 30% increase the flame speed. But energy you put it there is much higher than the energy you really that the flames even. So you can have a 30% enhancement by microwave to enhance flame speed, but the efficiency is really low. You rather put that energy into heat. To heat the mixture, and the flame speed is much bigger than that, right? So then what is the mechanism? So at that time I compute this thing. I compute that this is at the flame coordinate in this direction, and this is at the electron number density. This is at the reaction zone. You can hear the Q maximum is at the peak flame is here. You can see that the electron number density decrease probably exponentially or decay after the flame. So if you put a microwave there, an electron will be easily accelerated by electric field or microwave. So in front of the flame, there's only a tiny fraction of electrons because that's the flow that direction. And most of the electrons is behind the flames. So all the energy absorbed by electrons is after the flame. Okay? What you're doing? You're doing that you spend 90% of energy to heating the burning gas. You spend about probably 10% of the energy only heat that the electrons in the reaction zone or diffused into the unburned. So the efficiency is really bad when I look at this. And then I talked to Dick, and Dick, we got to do an experiment to find out what is the reason. If this is true, and then we better to stop doing this. And then we did the experiment there. So here is the experiment did by PhD and by Stockman. And he right now is working on Lockheed Martin. And then he's working with a methane flame at the equivalent ratio 0.76. And this is at a microwave cavity. So using that a Rayleigh scattering to measure the temperature. It's no microwave, and the microwave, you can see the flame front move down a little bit. That means flame speed is increasing. But if you look at the temperature, the green one is that is without a microwave, and then the dark one is that with microwave. The microwave generates 80 degrees in post flame temperature, and then has a very tiny effect in terms of pre-flame and a temperature profile. So therefore, that what do you see is really, you talked about a 6% flame speed enhancement. And really what you did is that is from raise the flame temperature by 80 Kelvin. So this 80 Kelvin is that is converted to 12 watt of energy deposition to the flame front, which is 50% of magnetic coupling efficiency. So therefore, that this is really that using a microwave and enhanced flame speed before the breakdown. Most of the mechanism is thermal. There's no ideating wind because the frequency is so high, right? And then most of the effect is because that the electron heating. The Joule heating effect. So the question is, how do I see the chemistry effect by microwave? How do I do that? You have to further enhance the electric field to causing that the electric field close to breakdown. So breakdown means that you have to generate electron avalanche process, generate high energetic electrons, right? And more electrons from the plasma itself, not relying on the electrons by the flame. And then you should be able to see the chemistry effect. And the gliding arc is one of the things, and then that means that I have we talked about it yesterday, with that I have a stable arc, and then I put a natural convection of flow, and I see this gliding arc. This gliding arc has more high electron energy, can do enhancement. This I showed you yesterday about how that the mode. So they basically see that you have a lot of chemistry effect generated OH by enhancing electric field. So all these things we see is try to conclude is that a ionic wind is a low-frequency electric field generated ionic wind that flow into both electrodes from a flame region due to the positive and negative ions. That ions can potentially modify the soot and NOx formation because it modifies the temperature distribution and modify the fuel and air mixing ratio. And the ionic wind and also generate flame instability due to the force field, Coulomb force generated by that one. And it can modify flame speed and reduce the temperature. And mostly that the ionic wind is not ionic, electric field it mostly affects the flame speed through the Joule heating effect. And electron Joule heating basically enhances the flame speed and increase the flame temperature. A microwave Joule heating in flames is not an efficient way because most of the energy is dumped to the burning gas. And a radical production by strong electric field could have the potential. But you have to raise the electric field close to the breakdown limit or pulse it. So that is the way and we have to do. It is necessary and to understand what is the kinetic effect of non-thermal plasma. So we are going to talk in the next lecture. We're talking the good more and beyond the electric field and the heating effect. Okay. Any question about ionic wind? I think this probably gives you a good picture about what my ionic wind will do and what it can do, what it cannot do. Right? Okay, good. So So in this lecture, we'll move a little bit further and to address what is that a chemistry effect and a kinetic effect. If it's just wind, it's just thermal, it's not that much interesting to us, right? It doesn't need a PhD to understand those things. Question?
About previous slides.
Yeah.
Is there an experiment on the plasma ionic wind on the supersonic flame?
Yes. They mostly on flow control, not on combustion, assisted combustion, because that the supersonic flow, the speed is 2 orders of magnitude bigger than the ionic wind. But the ionic wind can change the boundary layer of flow control, particularly on the aircraft wind flow instability control. Yes. Yeah. So what I'm going to talk, and is this a lecture, and I'll probably talk about slowly a little bit, and then. What? So the important chain initiation branching reactions in combustion. I think anybody who does combustion needs to understand what are the important chain branching reactions, right? Only you understand that, and you understand how to control the flame, because that the reactivity and then the flame speed, heat release rate, is governed by a few sets of chain branching reactions. And these reaction rates are so important and in governing the combustion process. Many people spend decades to measure one of the reaction rates to the uncertainty of 10% or 20%. So then the second question that what is the plasma chemistry? What is the time scale? If the plasma chemistry time scale is too slow compared to combustion, you don't do anything, right? If it's too fast compared to the combustion, you can separate them. You can model the plasma first and then model the combustion. If it's coupled, then you have to couple them together to understand it. And then what is the impact of plasma chemistry on combustion? And we talked a little bit in the previous class. We say that at the high temperature, mostly is thermal. And the intermediate temperature, they could help to produce radicals. And in the low temperature, it is even more helpful to produce radicals. But through what reactions? That question, right? And the diagnostics of plasma properties, and probably we'll not talk today, hope tomorrow. So I always say that we took that the chemistry class by Charlie Westbrook or Bill Green, and they will tell you that okay, there are a few chain initiation reactions at a high temperature. For example, this RH plus O2H abstraction reaction at high temperature normally happen about let's say 1100 Kelvin in flames. But this is the reaction is really slow, and unless the temperature is very high, okay. And the other thing that is the RH plus the lower temperature and high pressure, you form a lot of HO2. And this H2 abstraction by HO2 reaction is also very slow, and they form at the peroxide radicals. And this is again the reactivity of HO2 and they form H. All these things are very slow. So that means that compared to this reaction, H plus O2 reactions, the plasma maybe is slow in producing radicals. But compared to these guys, plasma is much faster. Because these are not energetic reactions. Plasma is much faster. If the problem is limited by chain initiation reactions, then you find, oh, I have opportunity. The opportunity is to using plasma to generate initial radicals and set everything go. That is one key thing in scramjet engine. Scramjet engine, when you come here, the flow is air with hydrogen, and the hydrogen does not have radicals to go, and you need some radicals to initiate that chain branching reaction. Then you need plasma to do that. Second, and the important branching reactions at 3 temperature range, H plus O2 reaction, which for hydrogen and for many hydrocarbons at high temperature flames, this is probably the one most important reactions of this H plus O2 branching reactions. So if you think that plasma reaction radicals production, plasma by electron impact dissociation, you can win this reaction rate, you can make a simple estimate. If you can win, you have an opportunity. If you can't win, then the plasma is only play a thermal effect. Okay? And then said, I talked in the last class, you said that the peroxide deconstitution, this reaction happened at 800 Kelvin to 1100, is quite slow. And plasma, energetic plasma always can win this reaction. So if you find that your problem, mostly ignition problem, is below 1100 Kelvin, mostly you are talking about ignition problem. Then plasma has a great potential to enhance the ignition process. If we talk about a low temperature chemistry and you want to control it in engine, for example, HCCI, you don't know how to ignition timing control is difficult. Plasma has the opportunity to control the ignition timing because the low temperature ignition is very easy. But the question is that how do you generate a good plasma to control a big volume, right? That is a key question. How do we design a non-equilibrium plasma can generate a volumetric discharge? They control the ignition. That's a different question here. And then if you think about plasma assisted combustion, it's very simply that electron impact with oxygen, let's say, generated 2 ground state of atoms. So that this atoms will, because this reaction, this is a process is quite fast, and then that reaction will attract H radicals, and then this one will generate a low temperature chemistry, because this one eventually, because 1 radical, you produce 3 OH radicals. This is a fast process. This is how plasma chemistry can do. And then the second thing that for electron impact oxygen, it generates a singlet oxygen, electronically excited. And this reaction, that reaction with this oxygen with H and generate branching reaction, this is much faster than this reaction. The same reaction, but this one probably at 300 Kelvin is 100 times faster. So if you can design a plasma, can generate lots of these guys, it would be great. You can do that. So, but to generate this, yesterday we said you only need 1 electron volt, right? Large electron volt is not helpful. But you have to control the electron energies around 1 electron volt. How do I do that? How do I create electrons? If I want to create electrons, I need a high breakdown. After breakdown, my electric field is really strong. I cannot optimize this reaction. The question is, how do you design a plasma discharge that fits this reaction? That is a technical question on plasma. We can share some ideas, and if you are interested. The plasma really created this kind of, not just this reaction. They create always different reactions and to accelerate a combustion process. So I try to summarize all what I talked about the process. And in hydrocarbons, any kind of hydrocarbon fuels, the reaction depends on the temperature. At high temperature, that the fuel, H abstraction, they go to these a C2H3 and vinyl radical. And then they go to this formaldehyde and directly go to HCl, and then HCl plus M generate H radicals and go to oxidation. And OH, H plus O2 reaction generate branching. So this is a high temperature process. In low temperature process, intermediate temperature, they go to a C2H3, and this C2H3 reaction with oxygen, they form H2O2, and they wait for a peroxide decomposition to form 2 H radicals, and this process is slower. And in low temperature, and then you go to the fuel with O2 addition, isomerization, and another O2 addition, maybe a third O2 addition, and this process is very small. So therefore, plasma can potentially affect this yellow lines and then green lines by generating this electrons, electronically excited species, vibrationally excited species, and then enhance these reactions. The question is that how much is it, and whether we can absorb it. So example is that this chain branching reaction, I create a new reaction pathway to accelerate it. For example, this methyl plus O2 reaction in methane reaction, this reaction is very slow. But if I can generate vibrational oxygen, and this reaction would be faster, so that I can accelerate methane oxidation at a low temperature by creating a non-equilibrium excitation of O2. But how do I do that? Excitation of oxygen vibration, you need a very small energy, electron energy. How do I do that? So that is all the things that you looking at the reaction. This is a slide shared by Andrei Starkovsky. He basically plotted what is plasma chemistry, and he said plasma chemistry is basically you can depend on the process. If you're looking at that the electronic kinetics, that the electrons and then being generated through the ionization process. And this electrons will be accelerated in the plasma, and then until they collide with the molecular and change the energy. So this electron in this process, ionization process, takes about a picosecond or femtosecond. It's a very, very short process, 10 to the minus 12. And this electron is accelerated in plasma, it generates electron energy distribution function, they call EEDF. And this electron gaining energy and then further ionize other molecules, and that takes probably a nanosecond around that. And then they recombine, they generate heat. This is a fast heating. So this is the electronic process. And we'll be looking at the ion molecules that they generate a rotation, electronic excitation, and this ion molecule, they always happen below 1 microsecond. So the plasma process is rather very fast, and it happens within 1 microsecond, and everything is done. And then you turn combustion process, and you take it much longer. Most combustion process is larger than 1 microsecond, and sometimes to a millisecond or tens of milliseconds. So what we understand well is that this combustion process, high temperature combustion process, is well understood, except the soot. Okay? And this ignition, low temperature ignition process is a little bit understood, but not to the extent we want to be. But in the plasma process, this process is also well understood, particularly for air plasma, nitrogen plasma, helium plasma. But the plasma process, coupling with combustion, that how does this electronically excited species or vibrationally excited species, they can couple with low temperature combustion process for fuel reforming, for low temperature combustion is poorly understood at that time scale. Okay? So the research focus really has to be here, not high temperature. It's really that a low temperature ignition fuel oxidation process controlled by a plasma. And then if you're looking at what is that the important reactions, and in air, then you have oxygen, you have nitrogen. So if you look at the potential energy curve of oxygen, and you can see that this is the ground state of oxygen, and then they can be excited into O2, singlet delta. They only require less than 1 eV, electron volt. The next is that is O2, electronic excitation to O2, a B sigma, is 1.6 eV. So you really need a very tiny energy to generate this kind of excited oxygen electronically. If the electron energy is very high, like a nanosecond discharge, it could be tens of eV. So then you can generate it from ground state to, for example, to this A sigma, and this is somewhere here. They can create that O2, a B sigma, if that energy is very high. So you can generate electronic excitation or directed ionization. So if you excite the molecule to here, this molecule will energy transfer will directly dissociate into a 2 ground oxygen atom, or 1 ground state, another one is at 1 delta. So depending on this energy, see, for high electron energy, you generate this kind of dissociation. For low electron energy, you generate this kind of molecular excitation. So what kind of plasma you need is dependent on the time scales, the reactivity enhancement you want to be, right? So the next thing that we look is that, that what kind of reactions will be involved. So we say that the electron impact reaction cross-section is that how big the reaction cross-section will be, and what is the reaction rate when the cross-section area governing that whether the reaction will occur or not. If it's zero cross-section, that means that nothing will happen, right? This reaction cross-section is highly dependent on electron energy. For example, this rotational and vibrational excitation, they only happen very high, particularly for oxygen, they only is 1 eV, around 1 eV. Beyond a few eV, you don't generate vibrational oxygen excitation. If you want to generate a vibrational excitation, your electron energy has to be small. If you want to generate this is at the 7 is here, is a singlet A and B, and then you want to generate radicals, and then O1D and O1S and ionization. You need very high energy. Then you need tens of eV, 100 of eV, and to generate this kind of thing. For combustion, you really don't need to generate this kind of high energy things. Really, you need to generate is this guys, and then probably the radicals, and then maybe the O1D if it is there. So the major enhancement in combustion in plasma, first, is that the electronically excited oxygen and then radical production of oxygen by electron impact. Okay, these are the major and number one effect. Number two, look at the nitrogen, because air always has nitrogen. If the electron impact oxygen, they must impact nitrogen too, because the nitrogen is 79%, right? Oxygen is 21%. So in nitrogen, you can look at the states. They don't have too much low states here. Nitrogen, you need strong plasma to generate 6.2 eV and A, B, C states. We generate a C state, it can relaxation to B state, generate your emission. You can use this emission to measure the nitrogen plasma temperature, okay, ABC state. So very different from oxygen and nitrogen, okay. If you want to work on oxygen, you need a weak plasma. If you want to work on nitrogen, you need a strong plasma, okay. This is something you probably don't learn in combustion. And this kind of electronically excited nitrogen has such high energy, they can break down the fuel molecules and can break down oxygen molecules as well, right, when they collide with oxygen. So if you excite electronically excited nitrogen, this electronically excited nitrogen can potentially dissociate oxygen as well, because the energy is so big. 5 electron volt is a lot. What is the UV light? Is about 300 nanometers UV light, near UV, right? Near UV. So what is the energy? About 3 to 4 electron volts, probably, right? So this is right that energy. So that energy can break down a fuel. So this is the energy. Oxygen is here, and AB, and the oxygen excited state is here, and the nitrogen is above. So when you try to design a plasma, you better to know what plasma electron energy is. You need to know the electron energy distribution in a plasma. Here is that a mixture. If we have a nitrogen and oxygen mixture, and then with hydrogen, for example, with this is that the energy loss fraction. Let's say I put some electron into it, where the electron energy is lost. It means that where that electron is putting the energy to generate excitation. So depending on electron energy, is E over N is a Townsend, right? The breakdown energy mostly is 100 Townsend, remember. The 1 Townsend and 100 Townsend. Those are the two things you may want to remember. If we want to talk to people about plasma, you remember the two numbers. Is 1 Townsend and 100. 100 Townsend means that something close is a breakdown threshold. 1 Townsend is about the vibrational excitation of something. So if you look at the 1 Townsend, this is a nitrogen vibrational state, and this is at a hydrogen rotation. This excitation, rotational and the vibrational excitation, basically happen at 1 Townsend. And 2, 3, about 5 Townsend, you can start to see that the O2 8 singlet, that reaction, and for 5 Townsend. And then if you look at the vibrational oxygen, you can see that the cross-sectional area of vibrational oxygen decreased dramatically. At 1 Townsend, you can vibrationally excite oxygen. At 10 Townsend, 1 order of magnitude smaller to excite vibrational oxygen, right? If you want to design a plasma reactor to vibrationally excite oxygen, you don't want this high electric field. You want to choose something lower. But once you increase that, but the nitrogen is very different. If you see the nitrogen, the peak around about 60 Townsend. Even the 60 Townsend, you can excite vibrational nitrogen. If you have a strong plasma, like a nanosecond plasma, you tell people that, oh, I generate a lot of vibrational oxygen, people will laugh at you. Because this is not correct, because the cross-section area of vibrational oxygen is very low at 100 Townsend, right? But you say, at 100 Townsend, I generate a lot of vibrational nitrogen, correct? Because the cross-section area is large. At the same time, at 100 Townsend, I generate a lot of O2 dissociation, probably the 2. So you see that O2 dissociation cross-section area is all right away around 100 Townsend here. So this is at the energy transfer distribution. And you have to look at this diagram to see what kind of plasma you want to design to work with air. So the next thing that what are the key reactions? If my electron energy is really large, I generate this kind of a vibrational nitrogen. I also generate that the electronically excited nitrogen as well. You only need about 5 to 8 electron volts to generate electronically excited nitrogen. So I say that electrons has high energy collided with nitrogen. That nitrogen generates a nitrogen C state. This C state has high energy. They collide with oxygen. They generate radicals. Or I have electrons directly break down this oxygen to dissociate oxygen into 2 radicals. So this is a radical production process. These 2 processes are the major reaction process we and in last year researchers understood in terms of combustion. And then vibrational excitation too. And if we generate a vibrational excitation, this vibrationally excited nitrogen could potentially react with some kind of H2O2, and then generated by a vibrational excitation can generate radicals. But this reaction pathway, I don't think that we proved yet. We still don't know to what extent is important. So let's see that what is the influence of vibrational excitation of low temperature kinetics is basically on the peroxide. This is that Andrei Starkovsky give me this figure. What he says that if you assume the vibrational temperature is equal to the transitional temperature, this is at the OH decay time. What you see is the model. This is the experiment. Measure that the OH decay time due to this peroxide. What he says that when you when you model including that non-equilibrium effect, that means that the vibrational energy temperature is higher than the transitional temperature, then the prediction start to make a reasonable prediction. So what that it says is that in a high energy, electron energy plasma, and you cannot assume that the vibrational energy of nitrogen or the oxygen is equal to the transitional. You have to make a 2-temperature or 3-temperature model to model vibrational temperature, electron temperature, and then transition temperature to appropriately model this process. So let's see, working back and forward. So this is very interesting and a finding by Andrei Stokowski. He gave me this slides. That's called hot atoms. Hot atoms is imagine that if you is that for some kind of a combustion process, people always said hot atoms too, right? If some kind of a non-equilibrium distribution of energy, you dissociate the molecule. One of the atoms could be very high energy, as higher the temperature is higher than the transitional temperature. For example, this process, if we look at the hydrogen diagram, if we say that this is the energy and this is at the hydrogen ground state, for example, if you have electron impact, you impact this hydrogen and right away excite to this state. As this state, let's say the hydrogen, excited hydrogen, they will relax and then they dissociate into 2 hydrogen atoms. But the energy was originally excited here, but after dissociation, dissociation energy is here. So the gap is this way. So you have this much extra energy still hold in the molecule that has to be dissipated somewhere, right? So this energy, 4.5 eV of this, after dissociation, is making this hydrogen very hot. That means that the transitional speed is very high, higher than the transitional temperature of surrounding mixture. Okay? Then how do we deal with this hydrogen, hot hydrogen? And how the same thing will happen for oxygen. If you have electronic excitation to generate electronic excited oxygen, if the energy is very high, they dissociate to 2 atomic oxygen radicals, but they have extra excess of energy. This excess of energy, they make that the atoms hot. That hot atom has high kinetic energy that will increase the reaction rate. So this a diagram. Basically, what it says that the super thermal atoms with high energy, they will change the reaction rate. So this is a diagram basically show you that what is that the plasma assisted combustion in hydrogen oxygen mixture. This is that basically hot atom with the O2 1D is that excited atomic oxygen, and this is probably O1D and something like that, and this is that other excitation. You can see that the model prediction basically the hot atoms and O1D and play an important role in terms of a plasma assisted combustion process. And same thing that the conclusion is driven here is also for methane oxygen system, and this a hot atoms and O1D production. So in a plasma, not only you have to worry about electronic excitation and then vibrational excitation, you also have to worry about these hot atoms produced. You make the kinetic mechanism so complicated to consider. But doing research and is try to find the most important ratio, right? You don't want to consider everything. I was in Bielefeld and probably last week, and we had a Bunsen conference organized by Professor Katharina Kosenhaus You know that she was the president of Combustion Institute. She organized a Princeton conference, invited a lot of people there. In the United States, we have 4 people in there, and Foking and me and Haiwan and Niels Hansen, we were there. And in Europe, they probably invited most of the chemistry guys. One of the questions, and in the last day discussion, is that how many reactions do we really need? And then recently, you can see that in Lorentz Livermore, and there's a real fuel mechanism, have 7,000 species, right? We probably have 10,000 reactions. And in the combustion research community, particularly with plasma, is that plasma gives you one more direction. How many species we really want? And they have different opinions in the discussion. There are people like Haiwan, basically, we don't need many reactions. We just need to fit them and find that the major ones fit them. There are people like researchers from Argonne. They basically think that we want all reactions. So in the end, the conclusion was that we need 2 different kinds of kinetic models. One is that science-based models. You put all the possible reaction pathways and reaction there. And second, we need a engineering application type of models so that it's very complex so people can use it. And the gap between them is that you develop efficient model reduction. You just, whatever model you have, you just reduce it. So that was the discussion and the conclusion of the meeting. And the example was that in someone from the surface chemistry side, they say that in surface chemistry, there are so many catalytic reactions, and nobody knows what is going on. So people try to put all this possible reaction pathway together, and then once you reuse it, you basically reduce it, and then to the extent you want to use. I kind of agree of this, but the same thing applies here for plasma. There are so many reactions. We really need to understand that, of course, understand every possible reaction pathway, but there's no end of it. But it really is that what are the major reactions? I just showed you a few, but we need experimental validation to show that these reactions are really indeed important, and that the major reaction ones. Then we can move forward to go to more details. So I stop here and I have you to take a break, and then we come back.